Good evening, everyone. Welcome to Problem Solving Session 7 for the NPTEL course Computational Fluid Dynamics. The course instructor is Professor Sreenivas Jayanti from IIT Madras. The problem solving session is handled by Anchor Karthika. So we'll just wait 2 more minutes before starting the session. Welcome back. So, in So till now we have covered almost half of the course in the syllabus. So like we have seen the flow in rectangular duct, triangular duct, and also the governing equations. Mainly equations for incompressible flow along with the boundary conditions. And in the last few classes, the syllabus was mainly focusing on finite difference approximations and also the consistency, stability, and convergence criteria associated with it when we are dealing with CFD problems. So in this week, the syllabus focus was on Navier-Stokes for compressible flows, solution of Navier-Stokes for compressible flows. So the problems are also associated with that. So we'll see what and how the problems were framed for this week. So in week 7, the on the topic of solution of Navier-Stokes problems for compressible flows, the main thing were about introduction to the solution of coupled and Navier-Stokes equations, and in that two main schemes were focused like McCormack scheme and Dean-Warming scheme. And after that, the stability limits associated with the McCormack scheme and the beam warming scheme were discussed by the professor. And also at the towards the end, the compressible flow to incompressible flow, how like if the methods are basically for compressible flows, how to deal with the incompressible flow problems. Also, the basic introduction was given on that. So the problems for this week's is first we'll deal with the uh, non-graded assignment problems, and then we'll move on to the graded assignment problems. This week's the main focus was on conceptual basis more than any problematic things, as you would all have seen. If at any point of time during this tutorial session you have any doubts, please feel free to stop and ask questions. And also, like, if you have any feedback on the tutorial session, you can always say. Yeah, now we'll start the session. The first question is, which of the following statements is correct about compressible flows? Any flow involving gas is necessarily compressible flow. Compressible flow equations are coupled but linear. Supersonic flows require either shock capturing or shock fitting methods for solution of governing equations. Okay, the question is basically which of the following three statements is correct about compressible flows. So we all know when we are saying compressible, we know like the density changes. So what does compressible flow mean in this context of CFD? If the density of the system changes, we say it will be compressible. So here, but how are we defining it with respect to the problems and in CFD? Any flow involving gas is necessarily compressible flow. In general, the thing is, all the gases are said to be compressible fluids. But in CFD, when we are talking about it, we generally denote compressible flow to be a property of the flow rather than the property of the fluid. So this statement is false. Next is compressible flow equations are coupled but linear. Yeah, the compressible flow equations are coupled but they are not linear. We all know that we would be solving the continuity equation and the momentum balance equations. So these equations are coupled flows but they are not linear. Non-linear terms are associated with it. Supersonic flows require either shock capturing or shock fitting methods for solution of governing equations. This statement is true. We'll see how this statement is true in the coming up slides. So the answer to this is we'll see what is the options given first. First one is option 3. This one is right. Next is option 2. This is not right. This is false statement. And third one is option 1. This is also a false statement. And option 4, it is 1 and 3. Since 1 is false, fourth option is also wrong. So the answer to question A is 3. Yeah, that is option 1. The third statement is right. Supersonic flows require either shock capturing or shock fitting methods for solution of governing equations. We'll see how this is true in the coming up slides. Okay, compressible flow here is not a property of fluid, rather it is of the flow. This we have seen now that compressible flow here denotes the meaning of flow. It is not of the fluid. And when we are seeing the continuity equation and the momentum balance equation in the x and y direction, it is dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y is equal to 0. This is the continuity equation when we are dealing with the compressible flow. Here, since density is changing, this statement cannot go to 0. And momentum balance equation in x direction is given by dou by dou t of rho u plus dou by dou x of rho u square plus dou by dou y of rho uv is equal to minus dou p by dou x plus dou by dou x of 2 mu dou u by dou x plus dou by dou y of mu into dou u by dou y plus mu dou v by dou x. And momentum balance in y direction is given by dou rho v by dou t plus dou by dou x of rho uv plus dou by dou y of rho v square is equal to minus dou p by dou y plus dou by dou x of mu into dou u by dou y plus mu dou v by dou x. I mean, it should be a common one, plus 2 mu dou v by dou y by dou y. And energy conservation equation should also be followed. I guess someone joined, right? Okay, fine. So this is the problem statement. I mean, we have seen this pointer options, laser pointer. Yeah. Momentum balance in x and y direction. Okay, we'll hide this for now. X and y direction and together with the energy conservation equation would also come into picture when we are dealing with the compressible flows. So basically, we are dealing with the coupled equation, but it is not linear. I mean, it is non-linear term. As we can see here and all, it is non-linear. It is not a linear thing. So the second statement is also false, where it is given that compressible flow equations are coupled but linear. Since it is given as linear, the statement is also false. So now we will move on to statement 3. Okay, what are supersonic flows? First of all, supersonic flows is the one where we have Mach number greater than 1. M is the considering M is the local Mach number at any arbitrary point in a flow field. If M is less than 1, we call it subsonic flow. If M is equal to 1, we call it sonic flow. If M is greater than 1, we call it supersonic flow. What is M Mach number? It is the velocity of the uh, fluid by the velocity of the sound in that medium. So supersonic flow, we have m greater than 1. In CFD, shock capturing methods are used for computing inviscid flows with shock waves. Shock waves are formed when a pressure front moves at supersonic speeds and pushes on the surrounding air. Consider when something is moving at a supersonic speed, that high speed, and pushes on the surrounding air, there will be a lot of deformation in the or discontinuities in the boundaries. So such methods are captured by using shock capturing methods. Um the computation of such flows is an extremely difficult task because they result in sharp discontinuous changes in flow variables such as pressure, temperature, density and velocity across the shock. Shock fitting consists in locating and tracking the motion of the discontinuities which are treated as boundaries between regions in which a smooth solution to the governing partial differential equations exist. So basically, uh, the computation of such supersonic flows is very difficult because there will be a sharp discontinuous changes in the flow variables like pressure and temperature, etc. So we are using shock fitting or shock capturing methods to locate and track those discontinuities in which are treated as boundaries in which a smooth solution to the governing partial differential equations exists. So basically, like these methods are used for tracking the supersonic flows. So third statement is obviously right. This statement is right. So yeah, now we move on. I hope this question A is clear. Now we'll move on to question B. Question B is, which of the following statements is true about explicit McCormick scheme? We will see the statements first. First one, it cannot be used for nonlinear equations. It cannot be used for viscous liquids. It cannot be used for unsteady flows. None of the above. So can anyone say the answer to this problem? Or you people yourself try it. Just think for a minute and try to give the answer because this is a straightforward question. Okay, before this, I'll give you the options also. Like, it is none of the above. The answer to this is none of the above because we basically know what explicit McCormick scheme is and how it can be used for nonlinear equations, viscous liquids, and unsteady flows. Basically, it deals with all these three, like viscous fluids, unsteady flows, nonlinear equations. So the answer to this problem is none of the above. we'll see how that is true. In computational fluid dynamics, McCormack method is a widely used discretization scheme for the numerical solution of hyperbolic partial differential equation. This second order finite difference method was introduced by Robert W. McCormack in 1969. It is a well suited for nonlinear equations, Invised-Burgers equation, Euler equations, etc. For all these methods, it can be very well suited. For nonlinear equations, this provides the best results. This method procedure or provides the best result. So basically, when we are dealing with explicit McCormack scheme, we saw how to formulate the problem in the for compressible flows. So it obviously deals with unsteady flows, and nonlinear equations are associated with the compressible flows. Compressible flows have nonlinear equations, so it is used to solve, and viscous fluids also it is solving. So all the three can be used for explicit McCormack scheme, and the answer to this problem is none of the above. Now we will move on to question C. Okay. Okay. Incompressible flow through a duct of constant cross section with adiabatic walls. Which of the following is constant? Volumetric flow rate, mass flow rate, pressure gradient, enthalpy. So which one do you think would be a constant in the flow through a duct of constant cross section with adiabatic walls? So the answer is mass flow rate, where other things like volumetric flow rate, pressure gradient, enthalpy, everything changes. So we will see the options first. Option 1, it is volumetric flow rate. Option 2, it is mass flow rate. Option 3, it is pressure gradient. Option 3, it is volumetric flow rate and pressure gradient. Option 4, it is mass flow rate and enthalpy. Since this is the only statement that is true, mass flow rate is only constant. Mass flow rate is present in option 2 and option 4, but in option 4 along with mass flow rate, enthalpy is also present. So the answer to this problem is mass flow rate. Is anyone trying to join the meeting? Okay. Okay. So we were seeing how mass flow rate is constant. So basically the density of compressible fluid changes with both position and time, and mass flow rate is constant because we deal with no accumulation terms. So mass flow rate in such cases remains constant. So the volumetric flow rate and the velocity also keeps on changing with position, but mass flow rate remains a constant. I hope this is clear. Now we'll move on to question D. In question D, it is asked that the conserved variables that are solved for incompressible two-dimensional flow are. The question is the conserved variables that are solved for incompressible two-dimensional flow are rho, u, v, w and t temperature, density and 3 velocity fields and the temperature t, or else rho, rho u, rho v and rho h. Or option 3, it is rho, rho v, rho w and rho et, and none of the above. Answer to this is option 3. Can anyone explain this? Like, it is a simple question where it is asked that the conserved variables that are solved for incompressible two-dimensional flow are. So when we are dealing with compressible two-dimensional flows, what are the governing equations that we would be solving? First one would be continuity equation, and second would be x momentum equation, and third y momentum equation, and fourth it is energy conservation equation. So we are having four conservation equations, and so we would be solving four variables. So obviously, since we are dealing with compressible flow, this option is wrong. It would be accompanying everything. So basically it is rho v, rho w, and since we are dealing with energy conservation equation, rho et, that is enthalpy. So option 3A is the right answer. So yeah, here we are normally for compressible flows, we are dealing with continuity equation dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v is equal to 0. And momentum balance in the x direction, it is given by dou by dou t of rho u plus dou by dou x rho u square plus dou by dou y of rho u v is equal to minus dou p by dou x and all the other terms here. And in similar manner, we are solving for momentum balance in y direction. And energy conservation equation also we are solving. So from this it can be seen that here it is, we are solving for rho, and here it is rho u, and here it is rho v, and from energy conservation equation we will be getting an enthalpy, that is Et. So it is rho u, rho v and Et. Or other dimensions would be rho v, rho w, rho et. Whatever it is, this third option is the right answer. So I think it is clear. Now we will move on to question E. This is the last question from the practice problems given as non-graded assignment. So after this we will move on to assignment problems. So in question E, it is asked that which of the following is true about the evaluation of pressure in McCormick scheme. It is, first statement, it is obtained from the continuity equation. Second, it is obtained from the momentum equation. Third, it is obtained from the equation of state. And fourth, evaluation of pressure is not necessary for compressible flows. So basically in the last statement itself we saw what are all the variables that are solved for when we are dealing with the compressible equation. So since explicit McCormick scheme is solving for compressible flows, we can see what are all the variables initially to solved is rho v, rho w, rho et. There are no pressure terms in this. So it is not obtained from continuity equation, it is not obtained from momentum equation, but it is obtained from the equation of state. And the last statement is also false. Evaluation of pressure is necessary for compressible flows. We cannot neglect it. So we will see that this answer is option 3. It is obtained from the equation of state. So basically one dimensional wave equation, if we are considering dou u by dou t plus c dou u by dou x is equal to 0. When we are dealing with McCormick scheme, the thing we will be doing is we will be having two-step solution, that is predictor step and the corrector step, and with a different scheme. If we are going with the backward scheme in predictor, the forward scheme would be followed in the corrector step. So we solve for the continuity equation for rho, x direction equation for rho u, x direction momentum equation for rho u, y direction momentum equation for rho v, and energy equation for et. And from these we can develop or we can evaluate pressure as function of rho and enthalpy. And similarly temperature is also evaluated as function of rho and enthalpy. So we are not separately getting from continuity equation or the x momentum or y momentum equation or even the energy equation, but rather we are solving it from the equation of state. So the answer to this problem is it is obtained from the equation of state. It is not obtained from the continuity equation, it is not obtained from the momentum equation, but it is obtained from the equation of state. And evaluation of pressure is necessary for compressible flows. We cannot neglect the pressure term in the when we are dealing with the compressible flows. So I hope these practice problems from the assignment is clear. Here we are using two-step procedure like predictor step and corrector step, where we are using a evaluating ui at n plus 1, and we are using this to get the original ui at n plus 1th time step, and we are taking the average between this and the previous time step values, and we are getting this. So basically this is how it is done in McCormick scheme. We will see this in the further in the problems, assignment problems. Now we'll move on to the assignment problems for the week 7. In week 7, a figure is given and it is asked that choose the correct answers from the options given below. Note that there are some questions with multiple answers. In previous thing also we saw like there are options questions where there are multiple statements that were right. So in a similar thing it is given, and in the figure it is given that compressible flow through a two-dimensional expansion in a pipe of circular cross section. So we can see that a pipe is there and after which it is kind of expanding, and compressible flow is occurring through this pipe in a pipe of circular cross section, two-dimensional pipe, but it is of a circular cross section. So now we'll move on to the questions asked from this week problems. So first, which of the following statements are correct about compressible flows? Any flow involving gas is necessarily compressible flow. Compressible flows are inviscid flows. Answer to this is option 1 or option 2 or option 1 and 2, and last one it is neither 1 nor 2. Obviously the answer is option 4, which is neither first statement is right nor second one is right. This one we have seen in the practice problems also. So can anyone come forward and answer this question? So previously also we saw how compressible flow here denotes the property of the flow, not of the fluid, and compressible flows are inviscid. I mean it is not necessarily true. So we'll see how these two statements both are false. While all flows are compressible, flows are usually treated as being incompressible when the Mach number is smaller than 0.3, where Mach number is the ratio of the speed of the flow to the speed of the sound in that medium. So what are inviscid flows? Inviscid flow assumption means that physically viscous shear and normal stresses are negligible. Thus, all of the viscous shear stress terms on the force side of the momentum equations drop out, as well as the normal stresses due to viscosity. So basically when we are saying inviscid flows, the viscous shear and normal shear stresses are negligible, but in compressible flows that is not the case. So compressible flows are not inviscid always. But what is compressible flows? Are they in gas flows? No, like in flows when the Mach number is less than 0.3, we denote it as incompressible flows. When it is above 0.3, we call it as compressible flows. I hope this is clear. While all the flows can be compressed, flows are usually treated as being incompressible when the Mach number is smaller than 0.3. So if this flow is very slow, at that situation we would be using the term incompressible. So the change in density would be very slow, like the particles moving are very slow, so the constant density cannot be changed. In such situations we call it as incompressible. I hope this question is clear. Now we'll move on to question 2. In question 2, what it is asked? In question 2, it is asked that which of the following are the is among the difficulties encountered in the solution of compressible flows. Coupled equations, non-linearity of governing equations, and determination of pressure. I repeat the question, which of the following is or are among the difficulties encountered in the solution of compressible flows? Coupled equations, non-linearity of governing equations, determination of pressure. And the options given are 1 and 2, 2 and 3, and third one it is 1 and 3. Option 4 it is 1, 2 and 3. From this we can easily say that the difficulties encountered when we are dealing with the solution of the compressible flows is mainly due to the coupled equation and the non-linearity of the governing equations. So can anyone say why it is not a determination of pressure? This one we saw previous problem also. It is because we are not getting the term pressure or evaluating pressure from any of the governing equations or the continuity, momentum balance equations or energy equations. We are getting the term pressure from the equation of state. Therefore, the determination of pressure is not a difficulty that is encountered during the solution of the compressible flows. So, the answer to this is the equations are coupled equations, and because of the non-linearity of the governing equations. So basically we will be solving the continuity equation for rho and x direction equation for rho u. So yeah, we can see here like sorry. Yeah, now it is clear that for continuity equation, we have one continuity equation, momentum balance equation, and together with the energy conservation equations. So these, from these equations it can be observed that these equations are first of all coupled equations, and also non-linearity exists in these equations. So basically the first one and second statements is right, like coupled equations and non-linear of governing equations are true. Therefore it is option 1 and 2 is the right answer. Now we'll move on to from this it can be seen we are solving continuity equation for rho, x momentum equation for rho u, and y direction momentum equation for rho v, and energy equation for et pressure we are getting from f is the function of rho and e. Like we are using equation of state to get the pressure, so it is a straightforward thing, and temperature also we are getting in a similar fashion. So determination of pressure is not a difficulty that is encountered in the solution of the compressible equation. So now we'll move on to question 3. I hope the question 2 is clear. If you are having any difficulty in any part of this question, please, or any part of the session, please feel free to stop and ask the questions. And your feedbacks are welcome at any point of time. You can give it over here or put it, if you are watching it in the YouTube, you can put it as comments. Now we'll move on to question 3. In question 3 it is given that consider the steady compressible flow through the diffuser section of a circular pipe shown schematically in figure 7.1. The flow may be compressible because fluid is a gas, velocity is high, pressure is high. Options given are 1 where fluid is a gas, Option 2, it is velocity is high. Option 3, it is pressure is high. Option 4, it is 1, 2 and 3. So here the fluid is a gas that is given in the question, I guess. Or even then it doesn't matter over here, because the compressibility of flow is mainly associated with the flow property. It is not associated with the fluid. Therefore, the first statement doesn't play any role in here. And the second statement that is given is the velocity is high. And this is a true statement, because we have seen that when the velocity is very low, the particle keeps moving slowly, and therefore we cannot compress it. Like it, the flow remains incompressible in such situations. The other way around, like when velocity is high, the particles moving in a very high speed, therefore it is compressible is also true. And in the last statement, it is the pressure is high. It also does not mean anything over here, and also it would not be this case also. We can see that here, like while all flows are compressible, flows are usually treated as being incompressible when Mach number is smaller than 0.3, where Mach number is the ratio of the speed of the flow to the speed of the sound in the medium. For example, if m is the Mach number is given by u by c, where u is the local flow velocity and c is the speed of sound in the medium. If velocity is very high, for example the local flow velocity is very high, Mach number will be very large, and the flow will be compressible. Like from here it is, if flow is very high, we can see that Mach number would also be very high, resulting in the compressible flow. But if Mach number is very low, I mean flow is very low, Mach number would be very low, and it would be smaller than 0.3, thereby becoming incompressible flow. Now we'll move on to question 4. In question 4, it is asked that consider the steady compressible flow through the diffuser section of a circular pipe shown schematically in 7.1. If the flow is axisymmetric and viscous, then how many partial differential equation needs to be solved to get the flow field? In this question, it is asked that consider the steady compressible flow through the diffuser section of the circular pipe as shown in figure 1. This is the figure 1 where compressible flow through two-dimensional expansion in a pipe of circular cross-section is shown. If it is axisymmetric and viscous flow, how many partial differential equations do we need to solve? So it is given that compressible flow. So how many equations do we need to solve? This is what we have been seeing from start to now. So it is obvious that we need to solve the continuity equation, and we need to solve the x momentum equation and the y momentum equation, because since it is two-dimensional, we would be stopping with this, and at last we would be solving the energy equation also, because we are dealing with the compressible flow. And so it is continuity plus x momentum plus y momentum plus energy equation. Together it is giving 4. So the answer is option 3, that is 4. This is the right answer. Now we'll move on to question 5. In this, it is asked that for the compressible flow case shown in figure 7.1, which of the following statements is true about the McCormack method? Before moving on to this problems, we'll take a 5 minutes break, and then we'll come back and we'll discuss how McCormack and another scheme, that is beam warming scheme, are differing and what is the basic procedure, because already we have seen through the lecture from the professor how to solve each of those. So we'll just have a quick recap of the concepts and then we'll move on to solve the problems, because since all the coming up problems are mostly based on McCormack and beam warming method. So yeah, we'll just take a 5 minutes break and we'll resume the session shortly. So yeah, we'll resume the session now. We have seen about McCormack scheme and the beam warming scheme. So what is the difference between them and how they are solved? We'll just have a quick conceptual recap so that it will be easy for us to go through the problems. McCormack scheme is a explicit technique. It is a finite difference scheme. I mean explicit finite difference scheme that we all know. In that we use the Taylor series expansion and proceed generally as we are solving, but in this we have a two-step method. One is the predictor step and the next is the corrector step. In predictor step we get the value of the variable at the n plus 1th time step, like n plus 1 bar we denote it as. And to get the original value of the variable at n plus 1th time step, we use the value that we have got from the predictor step and average it with the value we have got from the previous time step, that is nth time step, and average it and use it. In general, if the predictor is a forward method, the corrector would be a backward step. That is general thing. And if this is used for the compressible flows, what is the problem that we would be facing and why we are not preferring it? So the thing is, in McCormack scheme, we have one major issue. That is, this is an explicit scheme. So stability comes into picture in the McCormack scheme. How do we deal with stability in such cases is that we have to take a time step very small. That is, that time step should be very small, but since we are not able to get an exact analytical expression from this, we are not going for the exact one, and we are using a factor of safety f in the time step formulation for the Quran number. In that Quran number also we will be using the mesh Reynolds number. So by using all these things, we would be getting at the time step. So this McCormack scheme, for it to be stable, we should be using the time step in the solution process very small. It is not always practically feasible to go with such smaller time steps. So this is one of the issues that we would be facing when we are dealing with the explicit McCormack scheme. So to overcome this issue, another method is evolved. That is the beam warming scheme. Since we know that the compressible flow equations are the coupled equations, we should be solving for the solution of u. We would be needing the v values. So in beam warming scheme, what we generally do is we take we use the scheme so that it becomes implicit. We use the implicit method to solve that. For that, we need the value of the variable at I minus 1 grid space and ith grid space and I plus 1th grid space at both the values n plus 1th time step and nth time step. And we also do some evaluation procedure so that we would be dealing with the we would deal with the non-linearity by introducing another one concept. So basically, in beam warming scheme, by introduction of all these things, the method becomes implicit. So if it is implicit, we need not worry about the delta t, that is time step values. We need not like the size of the time step. But when we are taking a very large value of time step, the method would be becoming as we have seen in the first step itself, we would be required to know the values of u and v at all the time steps, so that would be practically a kind of disturbance in the solution in the beam warming scheme. So if we are requiring transient values with such higher time step, we cannot proceed. But if when we are reducing the time step, the method would be perfect enough. Or else when we want only the steady state solutions, at the time also we can go for the beam warming, implicit beam warming scheme. Both of these methods, that is McCormack method and the beam warming method, are second order methods. And also in beam warming method, we have one more form like delta form, that is a specialized structure used for the solution. These are all the basic concepts like differences between McCormack and the beam warming scheme. So now we'll move on to the problems given in this. We'll continue with the problems. So in question 5, it is asked that for the compressible flow case shown in 7.1, which of the following statements is true about the McCormack method? First one, it cannot be used because the flow is steady. Second, it cannot be used because the flow is viscous. And third, it cannot be used because the method can be used only for Cartesian system. So the options are: option 1, it is 1, option 2, it is 2, option 3, it is third statement, on option 4, it is none of the 3 is correct. So basically what we are using McCormack scheme for solution of the compressible flow. So it can be used for the steady. It is not false because it can McCormack scheme can be used for steady problems also. It cannot be used because the flow is viscous. No, this is also false because it can be used for viscous flows also. And at last it is given it cannot be used because the method can only be used for Cartesian coordinate system. That is also false. All the three statements are basically false. McCormack scheme can be used for steady as well as unsteady, and can be used for the viscous flows, and it can be used for Cartesian or any coordinate system. And so three statements are, all three statements are wrong. So answer is none of the three is correct. Answer is option 4. I hope the question 5 is clear. Now we'll move on to, okay. In question 5 itself, we have given some explanations. In computational fluid dynamics, the McCormack method is a widely used discretization scheme for the numerical solution of hyperbolic partial differential equations. This second order finite difference scheme was introduced by Robert W. McCormack in 1969. McCormack method is well suited for nonlinear equations like Invised-Burgers equation and Euler equations. For nonlinear equations, this procedure gives the best result. For linear equations, McCormack scheme is equivalent to Lax-Vanderhoff method. Like this is one more method used for solution of the linear equations. But we have seen all these things like it is a discretization scheme for the hyperbolic PDEs introduced by the Robert W. McCormack in 1969, and it is a second order finite difference method. It is suited for nonlinear equations by giving the best results for them. For linear also it can be used. These are all the takeaway points from the question 5. I hope the question asked in question 5 and the answers that followed them are clear for everyone. Like in this, it was asked question about which of the following statements are true about the McCormack scheme. Since all the four statements were false in the aspects of steady flows, also it can be used, and viscous flows it can be used, and for a Cartesian as well as other coordinate system it can be used. So all three statements are false. So the none of the three is correct is the given correct answer for this question. Yeah. Now we'll move on to question 6. Okay, in question 6 it is asked that for the compressible flow case shown in figure 7.1, which of the following statements is true about using beam warming method to find the velocity and pressure fields? So last problem we saw about McCormick scheme, and in this problem we are dealing with the beam warming scheme. For the compressible flow case shown in figure 7.1, the figure is the same that was given in previous slides. Which of the following statements is true when using beam warming method? So the first statement it is pressure is obtained by solving a Poisson equation. Although the flow is steady, we solve the unsteady form of the Navier-Stokes equation. Solution of the energy equations since we require only pressure and velocity. So, which of the following statements is true when we are using beam warming method to find the velocity and the pressure fields? Pressure is obtained by solving a Poisson equation. This statement is false. We will see how it is false in the coming up slides. And second statement it is although the flow is steady, we solve the unsteady form of the Navier-Stokes equation. This is true. We are solving only the unsteady form of the equations. We are not going for the steady form. And 3, it is solution of the energy equation since we require only pressure and velocity. So only option 2 is the right answer. So we are going with option 2, that is answer is option 2. We will see how it is in the next slide. Okay, what is, first we will have an understanding of the beam warming scheme. We are having a Navier-Stokes equation for the compressible flow actually, and implicit beam warming scheme, and we would be using the conservative, actually this one is given for compressible flows, so we'll just remove that and we'll just put it, we'll expand it. In numerical mathematics, beam and warming scheme or beam warming implicit scheme was introduced in 1978 by Richard Beam and Warming. It is a second order accurate implicit scheme mainly used for solving nonlinear hyperbolic equations. It is not used much nowadays. So, what is the procedure in beam warming implicit scheme is that when we are dealing with an equation, we would be consider we are solving the Navier-Stokes equation, and for that in general we would be proceeding, but like for we would be linearizing it, and we would at the end we would be using implicit scheme. So because of that we would be having a tridiagonal matrix or a structured matrix. So we use the algorithm to solve the tridiagonal matrix or so. So basically we are dealing with the we are dealing with unsteady form of the equation. We are not using the steady. We are not using going with the steady flow equation. Rather, we are using the unsteady form of the equation to solve them. And one more thing is, it is a second order accurate scheme, and since we are dealing with the implicit scheme, there would be no stability conditions associated with it. And yeah, basically it covers for getting an n plus 1th time step, we would be using nth time step values also, and putting all together, and we would be using a substitution to eliminate non-linearity if any in the system, and finally put it in the form of a tridiagonal, and we would be solving it. Or for the one dimensional case, and if the dimensions increases, the values, the diagonal structure would increase accordingly. And Since we are accounting the lagging, accounting the nonlinearity and also the coupling by using a previous time step values also. And this is the method for getting it if the solutions. So the although the flow is steady, we solve for the unsteady Navier-Stokes equation. This is the correct answer. We are not using the Poisson equation. In the previous one, we are not solving the Poisson equation to get the pressure. Rather, it is also obtained from the equation of state and the solution of energy equation, since we require only pressure and velocity. So I hope the answer is although flow is steady, we solve for the unsteady form of the Navier-Stokes equation. And in question 7, we will move on to question 7. In question 7, it is given that which of the following statement is true about McCormick scheme. It is conditionally stable. It cannot be used for unsteady flows. It can be used for linear equations. It is not applicable for viscous. It can be used only for linear equations, and it is not applicable for viscous fluids. So answer is obviously option 1. So we'll see how that is in a minute. Sorry. We know that McCormick scheme is an explicit scheme, so it is the conditionally stable. It cannot be used for unsteady flows. It can be used for unsteady flows. It can be used only for linear equations. No, it can be used for nonlinear equations. For nonlinear equations, it gives the best result. For linear equations, it is similar to some other algorithm. It is not applicable for viscous fluids. This is also false. It is applicable for viscous fluids. So only the first statement is right, that is it is conditionally stable. And stability criteria for McCormick scheme is given by delta T is less than or equal to F delta T CFL by 1 plus 2 by RE delta, where RE delta is the mesh Reynolds number. Given it is formulated by using finding out the minimum of two Reynolds number, where first is the U delta X by nu or V delta Y by nu, where nu is the rho by mu. And here one more term coming in picture is the F. F is the safety factor. Since we cannot go on finding a direct or stability criteria, we are using a safety factor F. And delta CFL is for inviscid CFL limit is given by is less than or equal to 1 by u by delta x plus v by delta y plus a times 1 by delta x square plus 1 by delta y square power 0.5, that is square root of this, and where a is the speed of the sound in the medium. So basically the stability criteria for McCormick scheme is given by this. So the answer to this problem is it is conditionally stable. We cannot go on giving the unconditional stability criteria for McCormick scheme, because it is a conditional stability exists for the McCormick scheme. So the answer to this is option 1. And the statement, McCormick scheme is conditionally stable. I hope this is clear. Now we'll move on to next question. Which of the following statements is true about beam warming method? First, it allows solution by marching forward from grid point to grid point. It allows solution by marching forward in time from time step to time step. 3. It requires intermediate evaluation in going from one time step to next. Option 4, it is none of the above. Options given are, we'll read out the options one more time so that it would be easier for us to understand the statements and arrive at the conclusion. Which of the following statements is true about the beam warming method? Option 1, it allows solution by marching forward from grid point to grid point. Second statement, it allows solution by marching forward in time from time step to time step. And third, it requires intermediate evaluations in going from one time step to the next. And option 4, it is none of the above. Answer is obviously it requires intermediate evaluations in going from one time step to the next. Everyone just recall what beam warming method is and how the answer to this is option 3. The next slide gives the answer. So before that, just take some time to evaluate it in your mind. Because no one is coming forward for answering the questions. So you people just do it by yourself and we'll see at the end. So we'll see the answer. Consider a one-dimensional wave equation given by dou u by dou t plus dou f by dou x is equal to 0, where f is u square by 2. So for simplicity purpose, we are using the term f here. And the solution is for this, when we are using beam warming scheme, is given by ui at n plus 1th time step is equal to ui at nth time step minus delta t into f I plus 1 at nth time step minus f I at nth time step by 2 delta x minus delta t by 2 times a I plus 1 n times u I plus 1 at n plus 1th time step minus a I minus 1 at nth time step u I minus 1 at n plus 1th time step by 2 delta x minus a I plus 1 at nth time step times u I plus 1 at nth time step minus a I minus 1 at nth time step u I minus 1 at nth time step divided by 2 delta x. So this is order of second order in terms of space as well as time, where a is the term introduced to move away from this. Sorry, a is the term introduced to remove the non-linearity in the system or eliminate the non-linearity. This is known as Picard substitution. So here we are using a at I plus 1th grid and I minus 1th grid, I plus 1 and I minus 1th grid, I plus 1 and I minus 1th grid to solve at nth time step. A is used at nth time step, and all other things are here we can observe that and ui at n plus 1th time step is there, ui at nth time step is there, and also ui plus 1 at n plus 1th time step, and ui minus 1 at n plus 1th time step is also there. So basically it is like we are using implicit scheme for solution of this. Thereby we can see that it is an intermediate. It is not going from grid point to grid point or one time step to another time step. It requires intermediate evaluations in going from one time step to the next. Like we are solving intermediate values also, and we are going by implicit method rather than marching from one grid point or one time step to the next one. So this is the question 8, which was dealing with the beam warming scheme. Now we'll look forward for the question 9. In question 9, it is asked that which of the following describes the beam warming method? First option is explicit second order accurate in time, second order in space, conditionally stable. And option 2, it is implicit second order accurate in time, second order in space, unconditionally stable. Option 3, it is implicit first order accurate in time, second order in space, conditionally stable. And option 4, it is explicit first order accurate in time, second order accurate in space, and conditionally stable. Answer is option 2. We know that beam warming scheme is an implicit method, so option 1 and option 4 becomes wrong. And we know they are second order accurate in time and second order accurate in space. So option 2 is the right answer, because in option 3 it is given first order accurate in time, whereas in real beam warming scheme is second order accurate in space and time. For example, we can see from this itself that is second order accurate in space and second order accurate in time. So implicit second order accurate in time, second order accurate in space, and also it is unconditionally stable. It is not conditionally stable, whereas it is an unconditionally stable method. So answer to this is option 2. Implicit second order accurate in time, second order accurate in space with unconditional stability. For example, beam warming scheme is a second order accurate implicit scheme mainly used for solving nonlinear hyperbolic equation. Beam warming scheme forms a tridiagonal matrix. For example, the structure would be in this form, where we can see that u at I minus 1th grid space, I plus 1th grid space at nth time step as well as n plus 1th time step is there. In the LHS side, it is like ui minus 1, ui and ui plus 1. All at n plus 1th time step is there. And in the RHS, it is ui plus 1, ui minus 1. Everything at nth time step is there, and ui minus 1 is there. So basically, this is forms the tridiagonal matrix, and it is and this system is a linear system of equations forming a tridiagonal coefficient matrix, and the scheme is unconditionally stable that we saw in the previous slides also. And there will still be oscillations, that is dispersion error will still be there when we are dealing with beam warming scheme. So therefore the answer to this problem is, it is beam warming scheme is an implicit second order accurate in time and second order in space with unconditional stability. I hope this is clear. Question 9 is clear. Now we will move on to question 10. in question 10 it is like given that uh, advantages of beam warming method over McCormick method is first one, it is applicable for coupled equations, and second it is applicable for viscous fluids, and third it accounts for nonlinear effects, and fourth larger time steps can be used. To give answer this question, we'll just quickly recollect what we have learned about beam warming method and the McCormick method so that it would be easy for us to identify the advantage of beam warming method over the McCormick method. So in beam warming, sorry, in McCormick method, it is an explicit finite difference method and given by Taylor's. In that we use the Taylor series expansion, and for it is a second order scheme, but wherein we go with predictor and the corrected two-step solution method, where in the predictor we use find an intermediate value at n plus 1th time step, and we use that value and average it together with the nth time step value to get the correct solution. And since this is an explicit scheme, what when we are dealing with the McCormick method, we have an issue of stability. So we are using a stability criteria that which we saw a few slides back, like yeah, this is a stability criteria where delta t is very low, where it should satisfy this criteria with delta t CFL, and whereas in beam warming method it was seen that it was an implicit scheme using we would be getting a tridiagonal matrix at the end, which should be solved to get the solution. And in beam warming method is also second order accurate in space as well as in time, that we saw over here. It is a second order accurate in space as well as time, and it is an implicit technique. And so because of that, beam warming method is an unconditionally stable. So we'll now look over the options and identify which one is the correct or advantage. In the first option, it is given that it is applicable for coupled equations. Both the schemes, beam warming scheme and the McCormick schemes, are applicable for the coupled equations. And the second one is it is applicable for viscous fluids. In the similar thing, both the beam warming method and the McCormick method are applicable for viscous fluids. And third, it accounts for nonlinear effects. It is also true like beam warming method and McCormick method both are dealing with the nonlinear effects, especially like we have seen in the last slides also. So these first three are not an advantage, like both are doing the same thing. Whereas in the last time option, it is given that larger time steps can be used. This is a true statement where it is advantageous to the beam warming method. Since it is an unconditionally stable, or like the stability criteria is not existing as it is existing for the McCormick method, so we can go for a larger time step in the beam warming method. So the answer to this problem is option 4, that is larger time steps can be used. So we'll just see that it is how it is given. Implicit method allows you to have large time step, because we have seen in this McCormick schemes criteria, stability criteria itself, that delta t here is very small, where it is given by f of delta t CFL divided by 1 plus 2 times of mesh Reynolds number. RE mesh is given by this formula where it is accounting for the minimum of these two. The first one is u delta x by nu, second one is v delta y by nu. And A and delta CFL is also another criteria where it should be less than or equal to 1 by u by delta x plus v by delta y plus A times 1 by delta x square plus 1 by delta y square times 0.5. This is a square root thing. So since delta CFL itself is already very smaller than this, and delta T should be smaller than delta CFL. So the time steps used in McCormack scheme is very small. So comparatively, it can be larger in beam warming method since we are dealing with the implicit flows. So in question 10, it is implicit method allows you to have larger time step, and option the okay, implicit method allows you to have large time steps in general, but the error introduced in having a large time step, the truncation error, may mean that you cannot put effort to have a very large step from an accuracy point of view. You will have to reduce a smaller time step. Like when we are going with a very large time step, the issue would be we would be having a larger truncation error and all, so we cannot have an accurate solutions. So from accuracy point of view, we should reduce the time step to a minimal thing. But if the interest is not in time accurate solution, we can take large time steps and then get to the steady state solutions. So, but in cases where we are dealing with the time accurate solutions, we need the time steps to be very smaller or optimal. But if we are not considering time transient solutions, and that is we need only the steady state solutions, in such cases we can go with the larger time steps and then get to the steady state solution. In those cases, if we are even if we are choosing a large time step, it would not be an issue. So that in that point of view, larger time steps can be used for the beam warming method, which is an advantages for the beam warming method over the McCormack scheme. So yeah, from in this, like the practice problems or the assignment problems for this is like week 7 is ended. Initially we have seen the non-practice problems, I mean non-graded assignment problems followed by the assignment problems. So in total we have seen the 15 questions in today's session. So in today's session we have seen with major focus on compressible flows and the schemes for solving the compressible flows like McCormack scheme and the beam warming scheme, and their stability criteria for both of them. We have seen that, followed by compressible flows and incompressible flows, how they are associated with the flows, not with the fluids, and how to deal with compressible. Like there are few methods. These are the few schemes for solving compressible flows. But if we are given with incompressible flows, how would we go about that? There are few methods. Like in such case, what would happen is that in continuity equations, there would not be density term coming into picture. The continuity equations would become del dot u is equal to 0, and there would not be any link between the continuity equation and the momentum balance equation. So there are few schemes specifically associated for incompressible equations like artificial compressibility, stream function vorticity scheme, and pressure equation scheme and pressure correction scheme. The first one is artificial compressibility scheme. It is mainly used in steady flow systems. Like you intentionally bring an additional term into the continuity equation and introduce a pseudo compressibility factor and so on. This would be seen in the week 8 problems, and week 8 would be dealing with those things. So this is for week 7. I hope every topic that was covered in the problems were clear and also the problems were understood. If there is any issues, please feel free to question and ask questions right now. Um, if any of you have any questions from today's sessions, please ask. Unmute yourself and ask now. Or you can even type it in the chat box. We'll have 5 minutes for the question and answer session. So we'll see if there is any questions. Okay. Sorry, can you just repeat it? Yeah, yeah. From NPTEL they shared a link, right? And that the PPT and the lectures, everything is present. They have already shared, or it is in the course page also, like the problem solving session. In that there is an Excel sheet shared. In that there is a link to all the PPTs. Yeah. Yeah. Like problem solving, any problems, or mostly focusing on assignment problems for that week discovered. In like you are attending, sir's lectures are separate, right? And that would be focusing on everything. And separate live sessions are for focusing on problems. Yeah. Do you have any doubt in today's session? Yeah, okay. Thank you. You can find these, lectures at the NPTEL site only. The tutorial session link for tutorial session would be, these would be uploaded in the YouTube, and the link for the same would be given in the Excel sheet. Together with the drive link for the PPTs and all. You can find it.
That problem solving sessions are also recorded one.
Yeah, the problem solving sessions are recorded. Yeah, they are uploaded in the YouTube, and the link is put it in the put in the Excel sheet, or it is in the, you can see it in the NPTEL site. And two other sessions are also being held, like Sunday and Monday. You can attend whichever is convenient for you, or you can watch on YouTube also, whichever is convenient. All three covers this basically the same with some different, slightly different problems. Yeah. Yeah, if there is no questions, you can leave. Yeah. So I guess there is no doubts or any clarification in today's session. So I thank everyone for attending today's session, and in a similar thing, we will meet next Tuesday at 6 to 8 p.m., followed by for the lecture, week 8 and the problems associated with the week 8. Um, so the lecture notes are being uploaded in the drive. The link for the same is shared with everyone. Please feel free to go over there and see for the problem solving session uh, videos, as well as the notes or the PPTs, everything. So everything is there. And if you have any questions, any clarifications, you can put it in the comments in the YouTube also. I would answer that. So yeah, mm, we were dealing with Navier-Stokes for compressible flows with main focus on McCormack scheme and the beam warming scheme. With and we saw how many equations and how equations are coupled. For example, the continuity equations and the x momentum and the y momentum balance equations, and also the energy equation that should be solved in the together with them. And the problems and the questions were conceptual from though McCormack and the beam warming scheme, with emphasis on questions also came from compressible two-dimensional flows, and what are all the governing equations, and all the what are all the variables that were solved for So yeah, that's all for today's session. If there is no doubt, we can close the session, and I guess everyone left also. So once again, I thank everyone for attending today's session, and you can drop your feedback also in the YouTube comments regarding these tutorial session. Yeah, that's it for today. Thanks everyone for attending it, and we'll meet again on next Tuesday at the same time, 6 to 8 p.m. Yeah, thank you.